Okay, I'm going to assume from the hush that's forming that it might be time to start. So without further ado, my name's James and this is Tristan. We both work at Virgin Media O2 in the network data science team, and today we're going to tell you a bit about simulations. So what can you use them for, what we use one for, and how you might approach making your own simulations. So without further ado, why simulate? This is really just kind of how I think of it. It's a bit meta. This is my mental model of mental models. So I think this is how we reason. You've got reality, which is always the ground truth, and then you form a mental model of how reality works, and you have an improvement cycle where you make some predictions about what you think is going to happen, like maybe it's a sport you're playing, like where do you think the ball's going to bounce? And if it doesn't bounce quite where you expected, you make a little adjustment to your mental model, which in this case would be your mental model of how physics works, and the next time you make a prediction you're a little bit better. Then you have the second loop, which is the decision optimization cycle, and you're using, in this one, you're using your mental model to make better decisions. So first of all, you're predicting where you think the ball's going to land, but the next thing you're going to be doing is like deciding where you want to put the ball. So you want to put the ball in the goal in the case of football. You'll use your mental model of all the physics, you'll line up your foot according to your mental model, or at least as well as you can line it up, and then you'll take the kick. Now, when you're making that decision cycle, probably this is not exactly how it works in your head, but you're looping through all the different actions you could take, like all the different positions of your foot, and you're deciding what the outcome would be if your foot was in that position, and then eventually you pick the action that maximizes whatever reward you want. So in the case of football, the reward, you get the points if the ball gets in the goal. So you pick one of the actions that leads, or the action that has the highest probability of that ball ending up in the back of the net. And I think that's how we reason, like probably some very crude examples here. So how does this link to simulations? Well, essentially, I think of simulations as just externalizing this mental model bit. So you're building your mental model in according to whatever rules you understand in a computer, and you're externalizing that mental model, and then you can do whatever you want with it to make decisions. So here's some example use cases. So in science, it's just like the first loop generally, like you're trying to understand reality and understand the rules of reality. So I mean, an example would be in particle physics, you design some rule, you put your rules of physics in, or at least what you think they are, you simulate things forward, you compare that to an experimental result, it doesn't quite fit, you come up with a new theory. Or AlphaFold, which is trained on many sort of experimental results of measured protein folds, and it learns how proteins eventually fold. So, and then you've got like the decision-making use cases, so the obvious decision-making use case here is reinforcement learning, where you're literally training a neural network on your simulation, and each update cycle you're adjusting the weights in the direction that where the gradient you're adjusting the weights in the direction which is increasing the number of points that you're earning each cycle, and then you actually have simulations that are used for humans as well. So like we are effectively reinforcement learning agents. An example of a simulation that trains a human would be, for example, a flight simulator. You really wouldn't want a pilot to have their first go in a Boeing 747 in an actual Boeing 747. So yeah, like you're training the pilots to make better decisions there. Power grid simulators, financial models. So now we know that simulations are useful. Hopefully I've convinced you they're useful in a very general sense. I'm going to hand over to Tristan now, who'll tell you a bit about what we used one for.
Thanks, James. So to frame the problem, so Virgin Media already has the UK's largest gigabit fast broadband network. We decided as a strategy we want to roll out even faster kit, so 10 gigabyte symmetric passive optical network all around our network, and that will give our customers a better offering, it'll be more reliable, it'll require less maintenance, which reduces costs, and also it'll help future-proof us against what comes in the future and anything our competitors might want to do. And doing this, though, involves our colleagues, like these guys here, going around our network, digging up roads, paths, whatever, And as I'm sure you can imagine, this is very disruptive, very time-consuming, and very expensive. So this program is a multi-billion pound, multi-year affair. So naturally, the company wants to know, what's the best way to do this. And there's quite a few things we need to consider when we're doing it. So what do our customers want? Where are they? What are our various budgets for different upgrades at different times? Other constraints around, what can our build partners do? There's only so many people around there who actually can go and dig up the roads and roll out the fibre and various things. But also nice ones. So about 2 years ago, Virgin and O2 merged, so there's nice synergies that are possible between the mobile network and the fixed network, so we can build those in too. And we're not the only game in town. We need to consider our competitors and what they're doing too. And layered over all of this, there's a huge amount of domain logic which is spread across a large number of people across a big organization like this. But one of the nice things we've got is that we have decided we're going to roll out fibre everywhere. We just need to decide how we schedule it, which makes stuff easier. So how are we going to frame that as a sort of data science problem? So whenever you're sort of tasked with the question, what's the best, what's the most efficient, what's the quickest, that's a really good sign that you're talking about an optimization problem. And so to frame this sort of rollout plan as a sort of optimization problem, we've got this sort of matrix here on the left-hand side. So down the side, you have all the various different areas. We could choose to roll out fibre in a period, and across the top, we've got, I've chosen rollout years here. And in each of these values in that table is a binary decision variable about do we roll out in that year, in that area, yes or no. So for example, in this example, we're rolling out in area 1 in 2024, area 2 in 2023, and so on. And to give you a sense of the size of this, Virgin Media serves millions or tens of millions of premises around the country. But you can imagine our network is like a big tree structure. And so we're lucky in that we can go a couple of rungs up the tree structure when we're doing this optimization. But we're talking about sort of cabinets which serve thousands of houses. And of those, we have, 5 to 10,000 of these cabinets across the country. So it's a big table. The rollout is a multi-year thing, so you can imagine, when you're talking about the number of permutations you have here, which is the number of areas to the power of the number of time steps, it gets big quickly. So that's framing the problem. We can also express budget limits and build capacities quite nicely as constraints. And then once we've got that, we can use a mixed integer linear programming solver to find an optimal schedule that maximizes some objective function. So before I go a bit more into detail on that, let's just do on a brief tangent about mixed integer linear programming, which is built a lot on Danzig's simplex algorithm. So if you haven't heard of this before, you might be surprised, but it's one of the algorithms that runs the world. It sort of chooses all sorts of things around you. And in essence, what you're trying to do is something like this. So maximize some objective function here, a plus b, given some constraints. So a needs to be between 0 and 34, b is less than or equal to 12, and you want 2a plus b to be less than or equal to 15. And it's just, this example. And you can probably, some of you might have already solved it in your heads already. I'm sure the rest of you could very quickly if you haven't. But the answer to that is you want b to be 12 and a is 1.5. And that is there, that's your maximum version. What if you have a million variables? This suddenly gets a bit harder. And that's kind of the scale we're talking about with this problem. And at that point, a linear programming solver is your friend. Simplex is a great is one of the core components of that, and that'll go through and find the optimal solution to that very nicely for you and very quickly. We have an extra wrinkle in that we're talking about binary decision variables, so we couldn't have, say, the solution here where a is 1.5, because what's 1.5 fibre rollouts? It doesn't make sense. So we need to have something which can deal with integers and sort of binary variables, and that adds extra constraints, but luckily there are mixed integer linear programming solvers out there which can help you do this. So there are a number of open source ones, and that's obviously where you would start if you want to use one. But there are also some proprietary ones too, which if you find that you need boosts in terms of performance, stability, etc. Anyway, back to the sort of scheduled programming. So one thing I mentioned there is you need an objective function to sort of maximize. And so what would that be for this sort of fibre rollout thing? What does the best fibre rollout mean? And so naturally for a company with a sort of a long-term investment decision like this, long-term profit is a very obvious thing to look at. So that's what we do. And so we simulate the network and business for a variety of different rollout scenarios, predict what that means in terms of cash flows, sum those all up, discount them to allow for the time value of money, and then we have a sort of value for that rollout scenario. But that's not quite what we want. We don't really care about the scenario. We care about the impact of the decision. And to do that, we then need a baseline. And so we also just simulate, what if we do nothing? What if we don't roll out at all? subtract one from the other, and you have the sort of delta, which is the specific value of that decision. And so to show what this looks like slightly more concretely, this again is a similar table, areas down one side, years across the top. And each of these values in here is sort of a mocked-up version of what the value of rolling out fibre in that area in that year would be. So here we're saying rolling out fibre in area 1 in 2023 is worth 450 quid to us, but it's only worth 370 quid if you wait till 2026 and things like that. And so the overall objective function is picking the combination of those decision variables such that the sum over these, well, multiplying that matrix with this one, and the sum over those values is the highest you can get, and you get basically the maximum long-term profit. But how do we come up with these numbers? And this is where we start getting a bit more into the details of the simulation. So we start off, as I say, we're all across the UK, and we break the UK up into areas which we can treat largely as independent things, which is nice. And then for each of those areas, we simulate our HFC operation, our sort of existing hybrid of fibre and copper, our fibre operations, which we're looking to roll out, the shared infrastructure, our competitors, customers who don't have broadband at all yet. And I'll come on to what we do with them in a sec. But then that's all wrapped in a sort of a telco object, which then knows information about the time value of money and a bunch of other things. And that operates across a large number of areas. And so we have, as I say, thousands and thousands of these areas. And then in each of these, we need to model our customers, what they're doing, their numbers, how their numbers grow, how they churn, our revenue, our various costs from maintenance, investment, all sorts of things, the response of all of these to our competitor actions, how all this evolves, and then also maintenance and running costs of running a network like this, because that's quite expensive too. And then once we've done that, we can extract loads of useful information about how our customers move, what numbers are at different times in different scenarios, and loads of cash flows as well, which we can then use to help make our decisions and also share information with our stakeholders too. So in essence, we end up with something that looks a little bit like this. So starting from the left-hand side, we have a local decision value simulator, which does exactly what we've been talking about. You look at all the different scenarios, model them out, and work out what that means in terms of the amount of money. That gives you a matrix like this of sort of your objective function, well, of, yeah, what making a decision in a given area is worth to you at a given time. You combine that with your constraints around build capacities and things like that, and to find a solution which gives you the maximum long-term profit by feeding that into your optimizer, and that gives you an optimal rollout plan, which we can then give to our partners to go and actually tell people where to build and do the important stuff. So we've got a model which sort of has a really relatively decent sort of mapping of what reality is for the business and various different scenarios, and it kind of gives us what we want at the other end. As I'm sure you've all seen this slide many times before, but you know, it's obviously not perfect in various different ways, but is it useful? Is it doing what we want it to do? And so the first thing it needs to be useful is it needs to be accurate in some sense. But it's kind of difficult to work out how good one of these deployment plans is because we haven't done it before, so you can't, look at historical, back evaluate it. What we can do is we can decompose our system into its component parts, the simulator, our churn models, some of our forecasting pieces, the revenue bits. And for those we do have more information, so we can evaluate those and see how well they are doing. And then we have to sort of combine them all back up into our various pieces. So we unit test the hell out of everything, how everything fits together. Obviously, we're making assumptions that we have connected things in the right way, and that's something we're going to have to keep coming back to. I'm sure as we evolve the model, that'll change at various points, but that's just something to be aware of. And once we've done all that, and we can estimate how good our solutions are according to how accurate we think our thing is. And what we found is that our optimized rollout values are hundreds of millions of pounds better than the naive rollout plans we might otherwise be doing. So we're pretty happy at this point. But as you all know, just because we've got a model which is saying, hey, good number, that means nothing in practice. So really now we need to start trying to realize the value of this, and obviously we need stakeholders to help us do that. So the crucial thing is you need to engage them really, really early. Make sure you know exactly what they want from you. Make sure they know exactly what you're doing, what all the components are doing. Go around the loop a few times to sort of round out various missing features and stuff like that. And having done that, they're really happy. They're going to take our solutions, run with them, and that's going to help drive Virgin Media's rollout. And they're waving our solutions around like He-Man with his sword. But the nice thing about this is not just a one-trick pony, so it doesn't just sort of optimize rollouts of fibre. you can also look at any other sort of network investment decisions you might want to do. So, where would you want to install this equipment, or what do you want to do about this scheme, or something like that. And if you can parameterize that option in terms of what impact it has on cost, revenue, churn, and sort of additions of customers, our tool will be able to tell you what options you should take and how good they are versus other things. So it's a really nice, powerful piece. But as I said, we're talking about large sums of money here with various different things, so we need to be very careful about what we're doing. So everything is obviously deployed in the cloud, nothing's running anywhere near anyone's laptops, and then all the information, metadata that's coming through everything is dumped out into BigQuery. So everything's auditable, and when someone comes back in a few years and says, why did you make me spend lots of money doing this, we've got some track record we can look at to say. And our users can self-serve some of the outputs of that using Looker, or we can dump off CSV so they can use the dirty green program if they want as well. So to summarize what we did, we've used simulations to help optimize the rollout of fiber. We've come up with solutions which are really good, we think. And in the process, we've created this sort of this network simulation tool, which we can use to scenario test for a whole bunch of other things. And we're looking forward to sort of expand that to lots of other areas, interesting problem areas, improve various models so that we can expand capabilities too. So the future is generally pretty bright, and it's, a really fun thing to do. So I encourage you to have a go. But I talked about what we did, so now I'll pass back to James, and he can tell you about how we did it and how you might try and do the same thing.
Thanks, Tristan. So something about me, I'm a bit of a closet engineer. I've never actually I did start my life once as an engineer, but I've been a data scientist for many, many years now. But I love talking to engineers and learning off them and learning how to code better. I think clean code is one of the most important things a data science team can learn and maintain. And so this is going to be very heavy on sort of engineering principles. Apologies if that's not what you want to hear. It's also quite dense, so like I'm going to skip over some quite deep subjects. It's more, treat this more as like a pointer, things you should Google if you want to know more. So without further ado, what libraries are there for building simulations? Well, there aren't many. There's a few notable sort of like honourable mentions here. There's Gymnasium that might come up in a search. It's not really for simulations. I've described that more as like a framework for training reinforcement learning agents, and it defines. Gives you a nice interface that if you did have a simulation, you could plug it into Gymnasium and it would handle your reinforcement learning. So it's not really for building simulations. SymPy. That's for event-based simulations. We weren't building an event-based simulation. We were doing discrete time step, so not really for us. And then there's Mesa. I looked at it. I saw that it was big. Big means complicated. I made a judgment call, or rather we made a judgment call, like, is it going to take longer to learn this than just write our own stuff? And we thought, yeah. So in the end, that's the library you need. So how to think about, like, this is obviously very big. Tristan did an excellent job of making it seem simple there, but there's a huge number of working parts, particularly in the domain logic, like many hundreds, if not thousands of lines of code. So how do you keep all this, how do you even approach this? It's like, where do you begin? I guess this has been called the Jeff Bezos approach before, of like working backwards, but like it works. I like it. It works in a general sense, not just for this. So start with value. Understand deeply how your tool and the decisions that your tool needs to make adds value to the business. Then understand the domain. Once you understand the domain, you can start developing sort of the elements of that, the salient elements that are important for the decisions you need to make in the domain code. You can then, once you've built your domain code, then decide the internal data model that maps to your domain code. And a little bit more on this later, but it's important to do it in that order. Don't try and build your domain around some arbitrary data model. And then, of course, try and get your big, messy, enterprise database into your nice internal data model. So that's generally the stages of developing a simulation. the next thing is like, how do you structure your code? Now, quick hands up, like, has anyone heard of the onion architecture here? Okay, so like, I'm going to say that's like maybe a fifth of the room. So like, this is definitely not instructions of how the onion architecture should be architected. Like, this is something to Google. I found it generally very useful in my career so far. It's not the only way to architect things, but in the right situations, it's very useful. What it does for you is it divides up your code base into more or less independent sections that people can work on independently of each other and understand how they interface. And that means that gets your team working in parallel. That avoids people stepping on each other's toes, and it keeps the architecture clean. You generally know where to look in the code base to find stuff. And like, as I said, I'm not going to explain how to do it, but the main principle is dependencies only move inwards. So you've got your internal data model here. That depends on nothing. You just define how your data should be structured. Then the domain, which obviously has to be parameterized by data, that can depend on the internal data model because it's below it. The application, which orchestrates the simulation and makes sure each time step moves and decides what happens in the time steps, and yeah, the application layer, that needs to know about the domain. So it needs to be able to instantiate domain level objects. And then you've got infrastructure, because as Tristan showed, like, the actual data lives in BigQuery and there's ways of getting it out of there, and then you've got to convert it into the right format. So the infrastructure layer only really needs to know about the application layer. But crucially, the application layer doesn't need to know about the infrastructure. Now, another term to Google is dependency injection. That's how the application level layer knows how to use the infrastructure layer, but doesn't have to know about it. Good term to Google there. The next thing is, I've got a really crappy short-term memory. I'm not very good at remembering anything rote. So what I tend to like to do is define some high-level principles or rules that you can use to deduce all the things you need to know, and then you don't actually need to remember stuff. And you don't, if you have a good set of principles that you've agreed with your development team, you don't have to micromanage either. You can just say, well, these are the rules we've agreed to, the principles, make decisions according to those principles, and more or less people make good decisions then. So what are the principles that we used? Well, the first one was we agreed that we wanted to make this agent-based, and therefore the coding paradigm was going to be object-oriented. Objects should map more or less to the main things and concepts, like one-to-one, so exactly how you intuit the world or the way that things work. Build your code that way. Then you know where to look for things in the code base. Components only interact via specific methods. This really was to avoid sort of side effects or things interacting with the internal state of other things. And yeah, like everyone's debugged code where you have side effects from functions, or things are interacting with stuff in unexpected ways, because that was just happened to be the quickest way to do it at the time. Well, then 6 months later you forgot that that's the little hack you did, and it takes another hour or two to work it out. So yeah, like, everything interacts via methods of the coding objects. The state of objects is stored internally. This is more just a convenience thing. You just make sure everything sits all together in one place. So, and it makes unit testing a lot easier too. So like, you can instantiate an object. You don't have to stand up a load of other data store objects around it. Only the objects themselves can update their own state. Again, this is just going back to, like, you don't want side effects. So like, if you're looking for how the state of an object went from, state A to state B, then you know that the only code you need to look at is the code in the methods of that object, nothing else. Nothing else can reach in and touch it. Use type hints for function inputs and outputs, or method inputs and outputs. Golden rule, like, you don't want to be guessing. Like, when you've got a huge code base, you don't want to be guessing what's going in and out. Which brings me to one of my sort of big bugbears when I look at sort of production data science code. Avoid using pandas in domain or application layers. Like, I love pandas, don't get me wrong, it's a great data managing tool, exploring tool. It doesn't belong in production, almost ever. Now, I'll make an exception to that. If you have to use pandas in production because it happens to be the right thing, maybe the methods in it make something a lot easier, or maybe you want to leverage some of the parallelization that they've built in, do so, but wrap it in a function and use well-defined inputs and outputs that aren't dependent on pandas. So then you know that if anything goes wrong in your pandas layer, like that function is all you need to test. You know what's going in, you know what's coming out, you can test it independently. Makes life a lot simpler. Use data classes. So that function that we just talked about, you'd use data classes instead. And I'm sure everyone's really, already knows about pedantic, but I love it. It's great. Use pedantic for your data classes. It also makes testing the data inputs, validating data inputs and outputs very easy too. Lastly, there's just good rules for life. Keep it simple, like don't make anything more complicated than it needs to be, and always unit test. If you follow those rules, then the instantiation flow is very easy. So here's a kind of very simplified mock-up of our internal data model. JSON here, like why not? You can pull stuff directly in and out of BigQuery with JSON. So let's say that's our internal data model, the one that we've mapped to our internal objects. Instantiating things is just traversing the JSON tree then. So the first thing you do is you build your simulation that everything goes in. Then you'd build your areas. The areas would look after building their internal dependencies, so the HFC operation and fibre operation according to this JSON file, and so on. Easy. How does control flow work? Well, control flow is just about one thing, a step method. So everything that interacts, everything that's an actor in the simulation has to conform to this actor interface. It means it needs to implement a step method. Now, so you've got a timekeeper object here, which looks after keeping track of the time. You've got a simulation which wraps everything. And what you do is you just loop through calling the time step method of the simulation object for every time step, and the simulation object cascades through all of the actors within itself, calling that step method. And if the actors have other actors within them, then those step methods are called by those actors too. So everything cascades, and essentially control flow is just a DAG like this. You'll probably want to record items of interest as time evolves. I've seen lots of messy ways of doing this. There's generally two relatively clean ways that I've found in my time, and I'm very happy to hear others. But so far with experience, you can either first of all, record everything in a data class. That just goes back to earlier principles. Here's a cash flow. It's parameterized by a type of cash flow, an amount, the time step it was incurred, and an area name. And then you can either append these data objects to an internal list, so the things you are interested in just get stored within the objects themselves, and at the end of the simulation you just cascade through and pull out anything that you're interested in. Or perhaps a cleaner way or a more scalable way, you can use a logger. So you just throw it in there, you log whatever you want, and if this is a very large simulation and you're doing it in the cloud, you can use logging tools like Cloud Logger, which then dumps all of these logs into BigQuery, and then you can do the analysis, produce your pretty pictures after or even during the simulation. How to avoid race conditions. This again is a very simple rule here. Just make sure that the state at time t+1 only ever depends on the state of other objects at time t. That way, every single time step can be parallelized without worrying about any race conditions. If you achieve that, then it's very easy to parallelize execution as well. So, very recently discovered an excellent library, excellent software package or library called Ray. If you've got your agents, so this is just a direct lift and shift from the Ray's website, but let's say that this counter here is one of your agents, you can make that calculate its next state in parallel just by adding this decorator to the class. And we did a POC on this, and it literally just works. It's amazing. And Ray also provides you with this nice cluster management software, cluster management dashboard, so you can watch the loads on however many CPUs or even machines that you've got, and decide, whether things are running smoothly. So Ray is amazing. It just works out of the box. It's much cleaner than the built-in multiprocessing, which we've had experience and trouble with in the past. So, yeah, highly recommend Ray. The interesting thing here, though, is if you're trying to parallelize, if you follow the rules of designing a simulation using pure Python and don't include data frames in it, you'll actually be surprised at the performance you get. Python gets a rap of being it's not that performant as a language. Like we managed to simulate sort of 50 or 100,000 different areas across a few hundred time steps, like in a matter of seconds using just pure Python. So like really wanted to use Ray. We did the POC to check it because we expected that we were going to hit processing time issues. In the end, we didn't need to. Python was fast enough. But just saying, if you need to parallelize, that's the way to do it. So to summarize, we've shown you, well, hopefully convince you that simulations are useful. We've told you a bit about how we used one. Hopefully giving you enough information to be dangerous, building your own simulations, and yeah, enjoy. I think we might have 5 minutes for questions, so if anyone's got anything. Hello there.
I think on the topic of keeping it simple, so Pydantic's great for areas of object interface for as a class. There's a library called SQL model that tries to bind the interface of SQL alchemy and Pydantic together to do the two things at once. Is that something you would advise, or is that something that goes against this principle of keeping it simple? Keep the validation of the object away from some state machine.
I haven't heard of this library, so I'm immediately going to Google it as soon as I get off the stage. It sounds useful in certain contexts. My immediate concern there is that it mixes the infrastructure with the internal domain data representation, and that would be against the onion architecture rules. So.
Thanks for a really interesting presentation. Was there a risk in the optimization method that you could find a local optimum that it wasn't global optimum? I'm not familiar with the process, maybe not. And then also, when you got a solution, did it make sense? Did you think like, okay, this is a rollout plan that is plausible and reasonable?
So the global optimum, local optimum. So first off, if it's just a purely linear model, you are guaranteed always a global solution because that's how the maths works. As soon as you throw in integers, it does heuristics and branch and bound, and there is a risk that you get to a local minima. If you're using there are parameters you can tune in the optimization to sort of increase or decrease the risk of this local minima being found. The trade-offs there, of course, being the faster you want it to complete, the less certain you are that it's global or very close to global. But what you can do in the optimization, there's something called an MIP gap, which tells you theoretically how close you are to how far away you could be sort of maximally from that global solution. And most of the time you don't need to get to global, you just need to get to good enough, and like within 1 or 2% of the global maxima, like given the kind of error bounds on our inputs, that yeah, we'd be happy with that. Lady on the front there.
So I noticed that a lot of what you're doing is obviously based on estimates of costs and depending on what will happen, and as well as how you're monitoring and reacting to say if you've actually overestimated or underestimated certain things.
I can take that. Yeah. I mean, yeah, that's a really good point that everything is, estimated and forecast and part of that. And so, yeah, we are in a sort of an ongoing evaluation and sort of tracking thing where we've worked out, first of all, sensitivities and what are our key inputs and things like that, but then deep diving, how good is our churn model, and we're going to keep iterating on making that better as we go on. So, yeah, there's only ever going to be an approximation, but it's just trying to have a continual process to make them as good as we can be, and yeah, at the moment they seem good enough, but we're going to keep trying to make them better and keep monitoring it to see what happens.
How many interactions with the
like you're bringing them some estimates that they're saying they don't make sense, or like how many times did you meet?
That's a really good question. So I guess it depends what you mean by the business, in that it's a big organization with lots of people. So we had some very close stakeholders who we were meeting, on a, not quite daily, but weekly basis, talking through all of these things very rapidly with them. And then as you get to higher level stakeholders and people with more specialist knowledge, then that was a sort of a slightly lower cadence, but still, as regularly as you can get them is often the sort of the best thing.
Involving them from the early beginning, all the stages helped a lot. So you didn't produce something that was rejected.
Yeah, exactly. They'll build the right thing.
Right. Just add to that, like the anti-pattern that we wanted to avoid was getting a specification, disappearing for several weeks or months, and then voila, we've made this for you. That's the anti-pattern to avoid. The ideal thing, as Tristan said, is like you want to pull stakeholders in, particularly the people who know about the domain. We are not domain experts, but we need to pull those people in and make them feel part of the team, or like basically into an agile squad. So yeah, their contact points are less frequent than the developers, but it's still weekly.
If I understand well, the way you approach the simulations problem, you essentially want to simulate an event, which was the aggregation of many sub-events. Is what you did to estimate distribution for each of those sub-events, and if so, you have to get kind of correlation among them.
So can I just check? To check the question. So is the question, how do we deal with uncertainty in the inputs?
When you have to simulate the event, there is the way you approach the problem of parameterizing the event. So for example, my event offers a gamma distribution with this parameters. And that obviously, because the event you want to simulate understand with the aggregation of actually not just one thing, but for example, the impact of revenue, the impact of costs, etc. So you estimate a distribution for all of these components, and then you, I guess you can do it again to a unique estimate. Is that how you did it?
Do you want to get this?
Summarize the question as well, please.
So I think the question is about how do we handle the sort of the distributions of inputs. I think for the mixed integer linear program, I mean, it just takes absolutes and solves. You're sort of, I think, happening upon an interesting question in general about solutions like this. Is like you've got uncertain inputs, but you calculate outputs as if they're certain, as if those inputs are certain. It is a future development area. There are techniques to get distributions of the decision of outputs from the simulation and outputs from the optimization. They come with complexity and compute time costs. Things you could do Monte Carlo, for example, on inputs according to the distributions of those inputs. But then you'd have to run the simulation and the optimization for every permutation that you, so like your sample rate would be very low. You might have to.
What would you do this not a Monte Carlo simulation?
No. We simulate. We simulate the decision space, and then the decision values, and then according to constraints, decide which decisions we actually want to take.
What I was going to say is, the dirty secret is actually that some of the stuff under the hood is actually pretty simple, which is obviously a bit frustrating, right? Because you obviously want to build fun, really rich models, but it's more important to get something useful, valuable in front of people, and then you can iterate from there to sort of build it out. And so those are obviously things we want to deal with, but I guess the principle we didn't say here is, get something out there, get something useful as quickly as you can, and then you can make it better from there. There we go. I think we're close to time now, but I don't know if there's anybody moderating.
One more. Anyone? Excellent. We answered all the questions. So thank you very much for listening.